All right, so a reminder, Monday is the first exam. I've got a few emails from people asking questions, what's going to be on the exam. I'm not going to tell you what's going to be on the exam, but I'll tell you what you should study. And as I hopefully have made clear, through the first two quizzes, the major skills that I kind of want you guys developing, are sort of mechanisms and synthesis, and this should all tie into reactions, right? And so at the sort of level of reactions, you guys got to know all these reactions, right? You need to, the back of each chapter, every single reaction that you see in the back of each chapter, there should be a summary, and so I would strongly urge you guys to make sure that every single reaction in the back of each of those chapters, whether or not they discuss them here, because clearly I told you guys at the beginning, we're not going to be talking about everything here. You've got my old videos, but even some of the videos might have missed some of these reactions. So every single reaction in the back of those chapters is fair game. So just make sure that you know them all. And from within those reactions, right, you go in one of two directions. On the one hand, what's the mechanism of them? And then on the other hand, if you know the reactions, you can start to begin to practice synthesis. And so, you can certainly expect to get a page worth, and you can look at some of my old exams just for a sense of the types of questions that I get. Unfortunately, given the fact that the material here is sort of the timing is a little bit differently than any other time that I've taught the course, you can at least get a sense for the feel of the types of exams that I like to give. I'll usually provide you guys with an opportunity to show me that you know reactions, so there'll be usually a few pages just full of, hey, what's the reagent for this reaction? Or what is the, so it's safer to put down the actual chemicals themselves. But know the chemicals necessary to carry out each reaction, and certainly, to the same extent, you'll be asked questions where here's the starting material, here's the reagent, what's the product? And so if you know all the reactions, those should be straightforward. If you find yourself getting confused about those types of questions based upon some subtle change, right? Some of the challenges can be, students will see, say, for example, a reaction on a ketone that looks like this, and then they'll see a reaction on a ketone that looks like that, and they'll sort of think that it's entirely different, right? When really your focus is on the functional group. So again, there's really no difference here. If you had a problem with this one, certainly you should be able to get a problem with this one. The differences with the functional groups that you might have to pay attention to are a little bit closer by. So I get that these are both the same. Well, I've seen instances, say for example, why is it that chemistry on this isn't the same as, say, chemistry on this, which is not necessarily the same as chemistry on this. And so there's a difference between different functional groups, right? And that's one of the things that you guys really have to sort of wrap your heads around. Yes, these are all carbonyls, but there's a reason that we give each of these a different functional group name. An ester, a ketone, an aldehyde, and that is because they behave very different in terms of the reactivity. And so you guys should be able to recognize that things like this aren't going to be all that different, but things like this certainly will be different, right? And so, we don't have too much at this point with regards to different functional groups. You have your alkenes, you have your alcohols, you have your carbonyls, right? As sort of subsets, and then from within those, then we get to the functional groups themselves. So that's that. So you guys should be able to know reactions, you should be able to know the products that form. Hopefully by this point, you're not you got to be careful how you're drawing the molecules, make sure you're not adding things that aren't there, recognize that you're seeing protons that aren't necessarily shown, and recognizing how many protons are at specific carbons. So again, I have no idea what the breakdown in terms of that's going to be, but you can expect probably at least 20 points worth of just questions like that. You can expect at least 20 points worth of mechanism questions. You can expect 20 points at least worth of synthesis. And so that's 60% right there. The remaining 40%, I don't know what it's going to be per se. It might be maybe you'll get a question that'll be a much more difficult mechanism question that'll really push you guys, or maybe a much more difficult mechanism question. Maybe it'll be a question about the fundamental basics of a general reaction, such as explaining, why a ester, is going to react with lithium aluminum hydride and lead to an alcohol, per se. But again, that's something that would be described through mechanisms. I'm trying to think of examples of stereochemistry. I don't know much if you guys seen much in terms of stereochemistry. Maybe reactions with epoxides. We haven't dealt too much with stereochemistry. Have we? I'm trying to think of stereochemistry. Well, inversion, yeah, it's anything that's new this semester. So certainly you know that SN2 transformations are inversion of stereochemistry. Certainly know about EZ elimination stuff. That's more first semester stuff that you guys already knew before coming here. I'm trying to think of the new material.
Just epoxides of the acid and the base thing.
Epoxides, right? So regioselectivity of epoxides, you could certainly imagine that would be a good question. So you should sort of know, but it's all based around the reactions, right? As we're sort of getting through this, we can clearly tell that it all starts with knowledge of these reactions, and that's really the way that this course builds off. It's expected at this point that you guys can draw molecules and redraw them and not be making mistakes, although I know that a lot of you still are making mistakes as you're trying to redraw molecules. It's expected that you can do that at this point, so I'm not going to be necessarily testing you on that, but every single question will be testing you on that because it's expected that you're able to do that to answer the questions. So really it's all about the reactions, mechanisms of reactions. The mechanisms can help you tell you about regiochemistry. They can potentially help tell you about stereochemistry in some cases, based upon what you've known previously, and then synthesis. So, yeah.
If you ask for a forward synthesis, then I'm trying to figure out the answer.
Yeah. So I'm not gonna ask you guys. If I ask you a synthesis question, I don't think I'm gonna ask you guys a synthesis question. I don't think. Maybe I shouldn't say this. But I don't, because I can change my.
If I figure it out.
No, I'm going to answer your question more generally, though, because I get the crux of what you're getting at. Most of the time, and I don't think, unless, I don't see myself doing this, but I don't think that I would ever ask a question where I would expect you to provide, to solve a retrosynthesis. Right? I'm expecting you to figure out the synthesis. Whether you figure it out by thinking forwards or thinking backwards, I want you to tell me a synthesis. Retrosynthesis and trying to practice retrosynthesis is a skill set that can benefit you. And so you can certainly expect to get a synthesis question. You guys have all taken the quiz at this point, right? Pretty much every single quiz, the synthesis questions could be answered in probably 3 steps. Sometimes maybe even 2 steps, right? You can expect that you're going to get a question on the exam that's going to require a bit more than that. And again, as I sort of said, that the value of retrosynthesis is that you can, it's just another way to think about the synthesis, and it's often very difficult to see 4 or 5 steps ahead, and so sometimes thinking in reverse. And sometimes you don't need to think the whole way in reverse. Sometimes you just sort of break it down a little bit, and you see in the product a certain functional group, and you say, well, this could come from this, this, or this, and you could just draw them out. And then as you're doing your forward synthesis, you can be like, well, that could be my target, that could be my target, or that could be my target. Which one would be the easiest to get to? And so it's about using the combination of those two. And no, I would never ask you a question where I say you can only solve this synthesis question through retrosynthesis.
That was not my
Oh, okay, that's what.
If I figure it out all the way through retrosynthesis, do I then need to write it back?
No. You have to make sure the reagents are there. And like I said, I think a lot of people get confused when they're doing retrosynthesis. They'll show the reagents that go with the retrosynthesis, where you're supposed to be going in reverse. So that's why I often said sometimes it's a good thing to do. You know, when you're doing the retrosynthesis, sometimes it's just a good thing to do, and this would sort of help solve the issue that you're sort of calling up just by drawing the forward arrow and putting the reagents there. And that'll be potentially just an internal check on mistakes that I've seen various students do time and time again. Do PCC when you mean sodium borohydride, we see, say, ozonolysis when really what you want is a Wittig, right? These are the types of things that if you did this, it solves both of those issues. So I think this isn't a bad thing to do. You don't need to. I'm not going to expect you to draw a forward arrow. You can just show the retro and then put the reagents above it. Either way that you answer, it's fine, but you just got to make sure that you're doing it right. What I don't want to see, and what you will be penalized on, perhaps extremely harshly depending upon the mood that we're in, is switching the problem around, right? I say make this from this, and then you make that from, you know what I mean? I say make A from B, and you go, well, right, so I want you to make A from B, and you go ahead and make B from A. You know what I mean? So you got to make sure that the question that I'm asking, that you go in the right direction, because, I don't know what you guys are thinking, and clearly that could be a very easy brain fart to have. But in the off chance that there's a question that's asked where it's much easier to go in the one direction, I don't want you to game the system in that way. Not that I would expect you to, or maybe even have that level of foresight to be able to do that. But just pay attention to what the question is asking. So, other questions? Yeah.
Actually, the question about the chapter
27? Yeah, so a lot of people have been asking questions about chapter 27. Chapter 27, you'll notice that I only put like chapter 27.1 and chapter 27.5. You're going to learn a lot about, if you take biochemistry, for example, you'll learn all that you need to know about amino acids. For the sake of this course, with the emphasis being on mechanisms and synthesis, you'll notice that the 27.5, unless they switch the chapters on me, but I'll tell you right now, what I was looking for you guys to focus on is this sort of idea of peptide synthesis, and specifically how synthetic organic chemists do peptide synthesis. So I believe in the chapter there is a very common coupling using a reagent called DCC, which is a reagent to take. Now you guys have probably learned, right? So you sort of know that if you take a carboxylic acid and maybe take an amine, right? If you heat it enough and you treat it to acid, right, you'll get the amide. Right? But this is kind of a forcing addition. There's actually much more gentle ways to do amide couplings that are much more effective, specifically in peptide synthesis. So you'll notice that amino acids are all chiral, right? And what you don't want to happen is, as you're doing your peptide coupling, you don't want to start scrambling the stereochemistry, which might happen under the forcing additions with just like acid and maybe heat or something like that. So chapter 27.5 discusses peptide coupling, which uses a reagent. There's a few different ways, but I believe that the book discusses this sort of the classical way, which is DCC. And what DCC is, so this is DCC, okay? And again, it's in your chapter, and I can just tell you right now that just yesterday up in lab, when I was sitting there talking to some of the group members, and who are often, in many cases, your guys' TAs for this course, I said I'm contemplating asking a question on the mechanism of this. Right? Right, so this, I think you use triethylamine or something like this. You know, so you should know this reaction. We didn't discuss it in class. It's 27.5. It's a reaction you guys should know. But really, that was that was what I wanted you guys to get from chapter 27. Is amide couplings, very important, classical, very important reaction, worth bringing up now because we're talking about carbonyls. We talk about ketones, we talk about esters. Let's very briefly talk about amides, and the most important thing, I think, in the most, certainly the most important thing in my mind for amides is how to synthesize them from molecules that you'll over time learn to make. And so now is the time to teach them, and you should see that the mechanism of this is a little bit different than what you've seen in the past. But ultimately, this is going to activate this molecule and effectively force dehydration. So go ahead and try that. We're not going to do it now. But you guys should know that mechanism for the exam. And I'm going to tell you it might be on there, and then I'll probably not put it on there, but I'll just let you know that we were discussing potentially putting this as a mechanism on the exam. So you can tell what I care about from that chapter. Okay? All right, so that's the most important thing for 27. Other questions? Yeah?
Just wanted to hear you say, which chapters exactly you're going to be focused on? I know it's 10 or 11.
So everything, you got to know every single reaction.
I know, but what chapters? Exactly.
Whatever's in my syllabus. Whatever's in the syllabus. What did it say? 16, 18, 19, 27, I think. 11, 48, 72. I had a when I was in grad school, I had a professor who really evolved. I guess I could say this is he's a ball buster, right? And he goes. Somebody asked that question, and they go, "What's on the exam?" And he goes, "Chemistry." They go, "No, but what specifically?" He goes, "Chemistry. I can ask you anything about chemistry, and you need to know it." I was like, God. All right, so I don't expect you to know everything, but yeah, just the syllabus. Everything, you know, the focus is on carbonyl chemistry. I think that where we stop is before enolates. I think the next thing that's going to be covered after the exam is going to be enolates. But you should know how to make an enamine, right? Certainly you should know how to make an enamine. But yeah, I think the enolate chapter, things like aldol chemistry, Michael chemistry, that's not going to be on this exam. But alcohol chemistry and all the other carbonyl chemistry prior to enolate chemistry will be on there. Yeah. And everything, sorry. And again, I may or may not, but it would certainly be fair for me to, in those reactions that I ask, to bring up a reaction from Organic 1 that you guys should know. Okay, so you got to make sure, again, it's all additive, so it's total fair game. Whether I do it or not, I don't know. I haven't decided yet. But I very well may ask, and it would be totally fair game for me to ask an Organic 1 reaction. So you guys got to make sure that you know that. Yeah, what did you guys learn? Yeah, double bond chemistry with alkenes, chemistry with alkynes. Yeah, you got to know all that stuff. Yeah. Grignard, yeah. So everything, we can. Yeah, any other general questions before we do some problem solving?
Last one.
This is we can do this. This might be challenging right now though, because this is classic enolate chemistry.
That's the old exam one. That's what's on your website.
Exam 1 from Organic 2.
Yeah.
Yeah, so remember, this is the first time that, so it used to be that the material, that's why you gotta be careful, because the material has changed. It used to be that, material that used to be covered in Organic 1, somebody made a comment that like, end of October of first semester organic chemistry is stuff that we're discussing now, so we were going through a lot faster. We can try it.
No, we could probably think it's more relevant to the exam. I just didn't know how to do that one.
Well, yeah, maybe because you need enolate chemistry. I mean, we could try it. There's probably a way to do it. I mean, it can't hurt to try it. Maybe not the second one. The second one was certainly...
I mean, whatever you think is more relevant.
I don't know. Let's see if we can do this. All right, so the question, and you'll see that you... Yeah.
I'm sorry, just about the exam. Is the format mostly just mechanisms, products?
Yeah, so know every reaction. Know every single reaction that's, again, you use the back of the chapters, the lists of reactions there. They're all fair game, dating back to alkenes, alkynes as well. Know the mechanisms of every single reaction. Understand if there's selectivity, whether it's regio or stereoselectivity, be able to address that and explain it if necessary. And then and synthesis. And so again, I don't know what the breakdown is, but again, like I said, you could probably expect, I'll leave up the other 40 points for my discretion, but you can certainly expect at least 20 points of reaction-based, like what's the reagent to do this reaction, what's the product of this reaction. You could probably expect 20 points just worth of that, 20 points worth of mechanism, 20 points worth of synthesis. You can expect at least 20 points of each of those, and then the remaining 40% may dip into some of those other and maybe more challenging, or maybe, I don't know. I haven't quite decided yet, but that's, yeah. So the question, and this becomes much easier with, I don't even remember what it was. Was it this? This. It was this. It was this. From this, right?
Two-step synthesis, I think.
A two-step synthesis?
I mean,
you can't. It's two parts.
products.
2 parts. Yeah. All right. So not quite this. All right. So the question was, and again, this I have no idea. We'll go through this and see if we can do it. If whether or not we can actually solve this problem or not using the chemistry that we know right now is sort of irrelevant. We can still go through the process of thinking about the synthesis and figure out. I'm sure that we can make this with the chemistry that we have, but the real easy way to do this is with enolate chemistry. And actually, to sort of make that point, somebody asked me in a synthesis question, and so I'll reiterate this. If there is a synthesis question, and you've, say, for example, have studied ahead, if you've taken the course for a second time, if you know chemistry from somewhere that's real chemistry, it's got to be real chemistry, but any reaction in a synthesis problem is fair game. You can solve any synthesis problem using the chemistry that you've learned, but if you want to use, it's got to be real chemistry. You can't just use magicine and say this is magic, and you can't make stuff up. But if it's a real reaction that you haven't learned yet, it's fair game. And that's rarely happened. Somebody once used this reaction that was McMurray reaction, which it's a way to take two carbonyls and put them together. It's effectively the reverse of an ozonolysis, literally. And somebody used that on an exam, and the reagent is titanium, I think trichloride, and I was confused at what they were doing at first, and I was like, oh my god, we didn't learn that, but that's what they're doing, is this McMurray reaction. And it's ironic because nobody ever uses this McMurray reaction, yet this person somehow learned it. But anyways, all right, so looking at this problem, let's spend a little bit of time, because I got to think about this a little bit. So why don't you guys all take out a piece of paper and pencil, and let's start by, I think what we probably want to do first, like we did last time with the ring, is focus on how can we make, what's going to be the way that we can make this ring. And off the top of my head, I don't know how we would do that, but I'm sure there's a way. So let's all think about how, let's do a retrosynthesis of this, because I think that'll help us a little bit here. Let's think in terms of retrosynthesis, and let's break one of these bonds. Now it turns out that this bond can be broken in a single step once you get to the enolate chapter, but we don't know the enolate chemistry yet, so we won't do that. You could on the exam if I asked the question that used it, but for now, we won't bring that up. Let's try to come up with a retrosynthesis that uses the chemistry that you guys have learned. So let's spend maybe like 5 minutes, and then we'll see what you guys come up with. And I'll just make one point to get your guys' brains thinking a little bit. One of the nice things about retrosynthesis, and one of the benefits of doing retrosynthesis, is you don't necessarily have to worry about selectivity in the reverse sense. And what I mean by that is, if you're going to do a retrosynthesis from this, say for example to an alcohol, you can do that. Why? Why can I not in a forward sense do this, but in a backward sense I can think about it this way? Yeah. Well, PCC will take this to that, right? But how would we go from this to that selectively? It'd be difficult. You'd have to use a hydride and you'd have selectivity issues. And so one of the nice things about retrosynthesis is that you don't have to necessarily, there are instances where you don't necessarily have to worry about the selectivity. So you could perhaps differentiate these two, which might be more difficult when you're thinking about synthesis in a forward sense. Yeah.
We're working backwards. You tend to draw your arrows pointing right in the opposite direction.
Yeah, so the retro arrow, this is just the way that people draw a retrosynthesis arrow. You can draw a single arrow in the reverse direction as well. This is just, you gotta get comfortable with this arrow. This is how you describe retrosynthesis. It's an arrow, it's that sort of double arrow going backwards. You just gotta get comfortable with it. If I flip the arrow the other way, it would say the opposite. So you gotta make sure you put it in the right direction.
Isn't it the same thing? Like, you're saying that we've got...
This is not the same as this. This is the same as maybe that. This is the same as the single arrow. You understand what I'm saying? So this arrow inherently applies retrosynthesis. So it means that you're making this from this. Sorry. Reverse that. You're making this from this. Sorry. Yeah. Whereas the double arrow going this way is saying the same thing, but just from a forward sense. So sometimes I'll ask questions and I might show that. Usually I'll do these arrows in synthesis problems. Yeah, so I hand up.
Wait, now I'm confused. Are we
Sorry.
making the one on the left or the one on
Yes, you're making the one on the left,
Okay.
using the one on the right as your starting material. And again, right now we're just going to try to break open the ring, so don't worry about if you can break open the ring and keep try to go with it. Right now, just try to open up the ring in some way. Once you sort of get there, I can take a look at what you've got. We can get some ideas. Sorry, well, in reverse breaking it. You know what I mean? Sorry, just let me repeat this so that we're clear. So, what I think the first step of this should be is you should think about how. I said breaking the ring, thinking in reverse, but somebody sort of. What I mean is, how are we going to make this ring? You know what I mean? And by doing that, we do a retrosynthesis in reverse, and the retrosynthesis will ultimately break that ring. And hopefully that'll simplify the problem for us a little bit. But you are doing a retrosynthesis. You're asking the question, what is the intermediate right before I make the ring? Right. Exactly. And then we can worry about breaking it down to isopropyl. Yeah, you're doing the opposite. If anybody thinks that they might have something, raise your hand. I'd like to sort of see what you guys are thinking. Yeah, so the question is the reverse of this is not this. Doesn't go into your practice. You just never thought so. So the fact that you went from, see what I'm saying? So when you sort of solve that issue sometimes is you put all the the same molecule and you break just with your eraser and you erase the bond and you're trying to make it go up the functional groups and you get it up. Okay, so we have we have an alcohol there. And one of the benefits of having the alcohol, we've got a retron, to make this ring, we have to be making a carbon-carbon bond. Right? We really don't know any ways to make a carbon-carbon bond to a ketone quite yet. But we do know multiple ways to make a carbon-carbon bond to an alcohol. So you can certainly think about those and what might be the starting materials of those. And then once you think about that, then you might ask the question, sort of second phase is, are there any problems with those in terms of side reactions? The other thing that you can ask yourself is, what are some other functional group modifications of this that we might be able to do? What's a retron of an alcohol that might lead us to a different functional group that might otherwise be valuable? Don't worry about isopropanol at this point. Just open up the ring and then we'll get back to the isopropanol. That'll be easy once we open up the ring.
Yeah, kind of stuff, but it's not even possible.
I would get a picture of drawing a greater bond and then drawing a nano. What I would do is I would just leave it as a negative charge. That mechanism in carbon bond and just eventually go as a plus. this, you should be able to so you feel comfortable.
Stuck there.
You stuck there?
Yeah. I remember.
Just count, make sure your targets.
Yeah.
6, 8, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
Oh yeah.
Yeah, it's just, but the strategy is he's got to fine tune it. Let's see some good strategies so far. Let's get to the ring structure. So I've seen a few people do it, both who recognize the need for protecting groups, which was good in this overall process. Bill did it from here. I'll just sort of make one more point if you're struggling thinking about how to break the carbon-carbon bond from here. I mean, I would say that that could also be a retron that could be helpful. How would you convert this to that? And why would we get the regioselectivity that we would? H2SO4 and water. This is a secondary. So this is one where you can do it, but you have to sort of think through the mechanism a little bit and think about the reasoning behind selectivity that we normally get. So, right? So usually you're not used to two carbons that are both sort of monosubstituted, right? Well, MCBBA would go to the epoxide.
Yeah, but you need to.
So, but H2SO4 and water would hydrolyze that, and you would get regioselectivity. And this, again, would be the type of question that I could certainly imagine myself asking on an exam. This is actually the perfect type of question. Maybe better for first semester organic chemistry because we're not really doing alkenes at this point, but this at least gives you a flavor of a question that I think would be a pretty good one. You guys have never seen this. You have seen this transformation, but perhaps what you hadn't been thinking about was the regioselectivity of this. And certainly, the regioselectivity that you would get would be H2O across this bond with the OH down there. The question sort of becomes, well, why? And there's a couple different ways, yeah? Well, pKa values of the alkenes, kinda. I mean, well, it's one alkene, so the pKa is going to be the same. It's maybe kinda, sorta. When we think about, yeah.
Do you want me to answer your original question?
Yeah.
When you add the proton, it's going to add to the beta carbon. Sorry. Oh, wait.
So of the two,
Wouldn't the positive first one be on that alpha carbon because it's resonance one?
is it?
But then why would it?
So your mind is going in the right place, right? You're recognizing not just Markov-Nikov addition, right? You're sort of saying, why do we normally get Markov-Nikov addition? We get Markov-Nikov addition because the resulting cation works. So this would be a perfect example and something that I would love to ask first semester organic chemistry students that do this chemistry, because you can't just memorize more highly substituted alkenes lead to the substitution. They are both the same substitution. What you have to recognize ultimately is the answer tells you that you want it there, right? Why might this be less stable? Or why would this be more stable than this? Yeah.
Because the carbon that's right next to it on the left has a partial.
Exactly, bingo. Right? Carbonyl has a dipole in that direction. So what you're doing is you got a positive charge right there, right next to that. So that is a destabilizing interaction. Thus, this is less stable, and thus you get the activity there. In fact, we could take it a step further and say, do you really think that you'd protonate this alkene? What do you think is the most likely to protonate? The oxygen. And this will be something that we're going to get into right? And now where is water going to add in? Well, it could add in here, but that's reversible. But what's the resonance form here? LAMO, right? So in fact, this is really what would be taking place, but you could argue it this way as well, and depending upon what your level of knowledge, where you are in terms of what you've learned, first semester might not know about carbonyls that much at this point, right? You certainly know that it's polarized. So anyways, that's sort of a question that would be, yeah. Like an alpha beta unsaturated? What do you think? So out of these options, I told you it's either this or this. What's that? Which is a more stable protonated form? So that's the question. Does it go after the? Let's hypothesize here. So the question was asked: how do you know that it's going to react with the carbonyl? Ask. What's your name? Davin. Ask Davin. He's the one that said no. It would protonate here, right? Ask Davin. Davin, why do you think?
Well,
I agree with Davin, by the way.
the structure on the right has that resonance form.
Right. So there's resonance stabilization. What else about this versus this that's sort of that key that we often discuss within relative stabilization? It becomes almost like a trump card. I don't want to use the term trump card. It becomes an ace.
Versus secondary carbon.
There's the positive charge on the wall, electronegative atom.
That's not good, right? It's not good. Bingo. Davin, on fire. Yeah, it's the octet. Full octet. Every single atom here has a full octet. That doesn't. Same reason, again, importance. If you ever struggle to sort of wrap your head around this idea of the importance of the octet rule, think about boron. Boron is less electronegative than carbon. It's less electronegative than nitrogen. It's less electronegative than oxygen, certainly. It's less electronegative than fluorine. Yet BF3, with another fluoride, that fluoride will coordinate and make the boron negatively charged, even though fluorine is the most electronegative atom possible. Boron wants to fill its octet. It will adopt a negative charge in order to fill that octet. So if you're ever questioning how important the octet rule is, think about boron. Okay? All right, so back to this guy. So this was just a point that I was making. So I've seen a few examples. Let me give you guys another maybe a couple minutes you have another option here that you can do a retrosynthesis from, or this one. I've seen a few people with this one. Again, recognize one point that we brought up previously about retrosynthesis, or about thinking about synthesizing molecules, and that's that we've learned a few different ways in which case you can make carbon-carbon bonds where the product has an alcohol. Now we're at an alcohol, so let's think about how we would do that. What does that mean? Refreshing that CPA. Exactly. Okay, so that if you had it in the presence of water, what would it make? Alcohol? Yes, sort of. More than alcohol. It's not just alcohol.
jumping into the next chapter, so you keep going alpha to carbon, alpha to carbon.
All right, so I've seen some good answers. I want to talk through a few things right now. I sort of want to make a point because this is something that I see quite a bit, and so this is one of the reasons why I like seeing your guys' answers, so I can address them, especially if I see the same type of, I don't want to call it mistake, but the same type of things happening that can hopefully clarify stuff for you. So it's very, I see this time and time again, and so if you find yourself doing this, just take note of it, and this could hopefully make your life a little bit easier. Okay? In a synthesis problem, it's not uncommon for students to fall in love with a specific reaction, right? And just use that reaction over and over and over and over and over again. The problem with that is you don't give yourself a level of flexibility that's necessary that might otherwise help simplify problems. And so I see this with quite a few people where you'll generate a nucleophile and they know that they can do this. Or let's just say RBR, right? The students know that they can do this. Right? So they know that they can attack an alpha halide with some nucleophile. So they'll take a nucleophile, some nucleophile they generate, and they will go ahead and they will treat it with an alpha halide because you learned this in first semester and you're comfortable with it. And hey, I want to make 2 carbon-carbon bonds. Well, I'll take this carbon that has a nucleophile, I'll take this carbon which has a leaving group, and I'll put them together and I'll make a carbon-carbon bond. And then you learn all this new chemistry, and you start applying this in instances where you don't necessarily need to. And I've seen a couple back-to-back people do this. And again, I don't hate this, but it would never work. And it's not necessary. So, few points. What do you guys think about this molecule here, first of all? How would you make it? Is it stable? I'm seeing somebody say no. Why? Why? What do we know about, what is one of the biggest things that we've learned in carbonyl chemistry? Especially right at the beginning, when we learned about hydrates, for example. Do hydrates like to exist? No, they're not going to exist. The equilibrium is always going to, almost, with few exceptions, it's almost always going to go to the carbonyl. And so that's 2 OHs on a carbon. You think that's going to survive? Absolutely not. What's going to happen? That'll break down to HBr in the carbonyl. But, as it turns out, you don't need that. Because the same product that you get to, and the same product that breaks down to, is the same one that would arise through nucleophilic addition with the carbonyl. So you don't need to do this. You add to the carbonyl. Get comfortable adding to the carbonyl. I got it backwards. To a lesser extent, but also the same thing, because it's not as, you might have a better shot of getting it to work, but again, it's less, it's not as, like you would never be able to make this. Very, very difficult to make. This is probably a little bit more likely to be able to be made, but hopefully you'll see the problem with this one as well. Is if you have an alpha alcohol, sorry, if you have a bromo, 1,2 bromo alcohol, whatever you're going to call this, and nucleophile is going to attack with this, that's going to get us to a molecule that looks something like this. Now, what's the problem with that reaction generally? You take a nucleophile and you treat it to this 1,2-alkoxybromide. What's going to happen? Is it going to react through substitution? What's going to happen? Is this reaction, you take a nucleophile, let's say a Grignard.
Would it be more elimination than the other one?
Would you eliminate? Kind of on the right track. So certainly there are acidic protons, but the proton that does the elimination is not the one that I'm concerned about. It's the OH. You will deprotonate that OH, right? This is the core of all the protecting group that we've been talking about, right? The whole reason that we introduce these protecting groups is because hydroxyl groups are very, 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 well, they're not very acidic, but they're certainly, if you treat it with a Grignard, the Grignard is going to deprotonate them. They're certainly well acidic enough that they're going to get deprotonated right off the bat, okay? So if you were going to use this as an intermediate, you can certainly make this, and in fact, unlike this, we've certainly learned ways to make these, right? But then what are you going to have to do? You're going to have to protect this. So then the question becomes, is there a simpler way to do that and to make that same disconnection? Epoxide, right? So I had this, right, that's going to ultimately get you the same. Ooh, that's bad. After protonation, you're going to get there. I had this, when I was in high school, I had a teacher who I love telling this story because it's I always have to be worried that it's going to sound like that I'm so I always have to be careful about how I tell this story so I don't offend people. But he was very he was very, let's just say, very versed in Confucius type proverbs, right? So all these lessons would be like, he's a mathematician. He took calculus with him. And he'd always say, if we use something archaic, he'd always say, I'm giving you a machine gun, but you're still using a bow and arrow. So that was what he would always say to me. So I think this is kind of that same thing. It's like, you've got this. You don't need to use this. This is going to be a little bit more complex. This simplifies it a lot more. Same thing with carbonyl. So you're learning these new reactions, and they're certainly going to simplify these syntheses a lot. So you should get comfortable using them, and you should start recognizing these types of things. Okay? All right. All right. All right. So we spent quite a time on this sort of discussing this, but let's discuss this. So let's discuss the alcohol. So again, a point that I tried making last week in regards to synthesis is alcohols, right? We discussed alkynes as good ways to make carbon-carbon bonds and to break up carbon-carbon bonds, and we discussed alcohols as good ways to think about breaking up carbon-carbon bonds. And so we kind of did that right away for you. Right? We've got this molecule that's got an alcohol on it. And so once we have that alcohol, we start to think about these carbon-carbon bonds that we can make. We've got options, right? There's several carbons that we can make. Oh, this is great chalk. Just use this, although I don't use this. But those two that I just labeled in yellow, how are we going to break those bonds? Yeah, I mean, maybe let's just think on the surface, and then we might have to go back and adjust accordingly and rework it a little bit. But certainly you can imagine, at least conceptually, that these could come from Grignards. And so there's a couple options for breaking these. MGBR. So I've seen a few people, let me make this point because I've seen a few people do this. And so I'll just sort of correct it because I can sort of explain how there's confusion. I'll see a lot of people doing this. Not sure if you've learned it in a certain place. And it's not horrible, but to me it implies something different than it is. To me, what this implies is almost a dianion. Because there's two electrons that are reflected here, which when people draw it this way, I think aren't thinking about it. So I don't like it when I see you guys draw Grignards in this fashion. Either draw them like this, right? Don't put the negative charge anywhere on it, and then do the chemistry from here. Or what I like to do, because I think it's helpful to show those lone pairs, is just not show that bond, and to make it as if it's an ionic salt, like that. You guys, does that make sense? Because you're implying, this inherently implies that there's a set of electrons in there, so it's almost suggesting that this is dianionic. So don't try to get out of the habit. I've seen quite a few people drawing it this way, so I'm wondering if you're learning it somewhere. Break that habit. Draw them this way, or my preference is often this way, because it's a little bit easier than to show their nucleophilic attack, okay? All right, so we could have that one, or we can break this bond. So this would be A. This would be B. And as luck would have it, and so as we look at these two molecules, it turns out, you'll find out next, after the exam, that this is actually perfectly cool to do. And in fact, this is probably the best way to do this. Because what this is the resonance form of this is the enolate, which we'll learn about before. So this is actually how you would do this. Ordinarily, let's use this as an example. Why might I have a problem with this guy up here on the top? No, there's, I'm not that nervous about this. So the resonance down here, again, this is next semester. Or sorry, not next semester, this is next class, or after the exam, right after the exam. That's totally cool. So this is the enolate, which we'll learn about next, in a few classes. And that, in essence, makes this a fine reaction to run. I'm a little bit more concerned about this one. Yeah, so, and again, it's not going to attack it, it's probably not going to attack it in an intermolecular fashion because you've got a 6-membered ring versus a 4-membered ring. But it's probably going to cause problems in terms of polymerization and all these other things. So you might be okay, it might end up working out okay. But you may want to revisit this and maybe protect, say, for example, this carbonyl, right, just to play it safe. So, in fact, if you were going to go that route, what you might want your first electron to be, and I saw somebody do this, which was good, is they protected that, and then either way that you go, you're in good shape, okay? So that's one of the ways that you could break this molecule down, and we can revisit that in a second. But I want to sort of get back to the other way. So we showed A and B there in terms of Grignards into a carbonyl. But again, once you see that alcohol, you should recognize that there is another consideration. There's another carbon-carbon bond that you could think about making, right? And it's the one that's one further away, right? So it's this guy here, or that guy there, right? So, you know, this would be, and again, you just draw it out, and then you ask yourself if there's any problem with it. And again, this is one of the things about retrosynthesis. Don't worry at the beginning. You know, you sort of draw out how you would break that up, and then you look at it, just like we did before, and we ask ourselves, well, is there any problem in this that we might need to address. Might one of these be better than the other? Yeah.
Would that be your only starting material?
Yeah, well, we're not going to worry about that. If there's time, we may never get around to breaking it down further. Maybe I'll ask it on the exam. But if we have time, we'll break it down. But the point is, we're just trying to simplify the molecule first, and the quickest way to simplify it, we've got to open up the ring at some point. So that's why we're focused on that. At some point, then once we get there, then maybe we'll worry about breaking it into 3 pieces, 3 pieces, and 3 pieces, and then from each of those, we'll worry about how we make those reagents of 3 from isopropanol. Right, so one option would be something like this. Right? One option would be that. The other option would be right? So the other option will be that guy. Okay? So you see what we did here? So this is going to make this bond and subsequently form the alcohol there. This one's going to make the negative charge there, and it's going to open up the other way. Again, I don't really love either of these. You can't really make, I don't know that you guys have really seen this or not, but you don't generally make Grignards at this position. There is some what we call Oupolon chemistry that would actually be really useful here, where we could use that as an aldehyde and we can open up, but again, that's chemistry that we haven't learned yet. But generally, you can't make a Grignard from, say, an acyl chloride. It's not something that's generally done. Thus, we'd have to maybe consider that coming from, we could do that, but how might we overcome that? If that can't be an aldehyde, if that can't be an alcohol, maybe it could be an alkene, but then we're starting to add carbons and it's just going to complicate this even more. So I don't love this. This one, maybe it's okay, but again, we'd have to protect that as well. But again, you sort of draw them out, you think about what the compounds are that are there, you assess whether or not these seem reasonable, and then you sort of move forward with the synthesis. All right? But again, the bigger point that I'm trying to make here is that you see the alcohol, you should start thinking about how you would make those alcohols and start thinking about epoxides and carbonyls. All right, so we've only got about 10 minutes left. We have a few options. We can either take one of these pieces that we like and try to break down the synthesis further, or we can go over something else. Because we spent the whole class on this. You want to keep breaking this down further? Keep practicing? All right, so the piece that I think I liked the most out of all of these was, I think, I'll do this one just because we don't know enolate chemistry yet. So I'll do the aldol, but I won't do the enolate just because we haven't done the enolate yet. But keep it in mind in terms of enolate chemistry. This isn't the one that I like the best ultimately, but it's one that we can think about. So this was one of the retrons that we discussed. Right, we would make that Grignard, it would react intermolecularly. But now what we have to do is, looking at isopropanol, our next goal should be, well, what's the retron from this? You guys should all be able to tell me the retron. We might as well just quickly draw the bromide, exactly. So let's just get that out there real quick. Right. Maybe we have to make ethylene glycol from this as well. Whatever. We won't worry about that right now. So looking at this molecule, what we kind of need to do right now, and what I would do is I would look at the product and I would see isopropanol. And our first goal was to open up the ring. The next goal I think would be centered on how do we, big picture, break this into 3 carbons and 3 carbons now at this point. And so those carbons that we're really looking at ultimately are those guys right there, right? So we need to figure out a way in which case we can make this bond. And looking at this molecule right off the bat, you guys see any ways that we can do that really quickly? Huh? Are there starting materials that you think could make this fairly easily, like just in a single step? Not quite sure.
Grignard attacks an aldehyde. Add carbon. Carbon.
Grignard attacks an aldehyde.
Which one affects like the other carbon, the other
So hold on. I'm going to go with that thought. So let's, again, we're not going to worry about whether it's feasible or not. We're just going to reflect, and then we can tweak it a little bit, but that's kind of what we want to do. You're not going to be able to make this directly from the aldehyde, but you can make that in principle from, well, let's talk about it. So that would ultimately be the retron, right? Because you'd want to oxidize this and do the glycol addition, which, see, I think we're not really doing a retrosynthesis here at this point. So the problem is that you would need to oxidize, to get to there, you would need to be there. And so it's going to get very steppy, because now you've got the 2 carbonyls. It might be tricky, because you're going to then have to play around with the oxidation state of that.
Wait, can't you just use PCC of an alcohol to make it ketone?
You can, but how are you going to protect, so you want to make this ultimately, right? How are you going to protect this in the presence of this? You can do this, but you need to, if this was your molecule, you'd maybe need to do sodium borohydride first, and maybe hope that you would get selectivity, which you could argue, I'll get selectivity for an aldehyde over a ketone with sodium borohydride. It's a little bit slower, so you could maybe make that argument, and maybe I'd buy it. So you'd say, well, I'm going to reduce this, then I'm going to protect that, and then I'm going to reoxidize that. So it's a bit steppy. You could, I guess, do it, but maybe there's an easier way.
Well, did you go from that first molecule into detecting the aldehyde and then making a carbonyl again, and then attack it?
See, but again, then the question becomes, so you want to protect that guy? Again, I almost feel like you have to go through the alcohol.
Well, you go to an alcohol first, and then you do CL.
I don't think we have a choice. I kind of think we do have to, I kind of feel like we do have to take care of that, which makes this a little bit of a tough one. We don't have to too much time. Huh?
That's why I take this route. I don't like 2 functional groups inside 3 carbons.
Yeah, we've only got about 5 minutes left. This is probably not. I think it's clear that this is going to be a very, 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 very steppy route breaking this down further. I think the enolate way would have been way better. Ultimately, that was the question that was on there. And so again, this is maybe an example of maybe the lesson to be learned here is maybe not necessarily for this exam, but down the road. Here's a perfect example where if we could just do enolate chemistry, this would be done in 2-3 steps. If we ignore enolate chemistry, yeah, let me do that. Let me show you. I just saw somebody go, really? Yeah, you could. Watch. So if your starting material, so if that's your starting material, in fact, it's even easier than this, because you can break this up directly through a reaction that you're going to learn shortly called Claisen condensation. So that right there, if you take this, as we'll see, and again, you don't need to know this, but I'll just make the bigger point that you're going to learn new reactions, and you're going to see how knowing these new reactions will make synthesis. You got to choose the right reagents for the step. This right here, this right here can be made through Claisen condensation, okay? And then from there, if you want to break it down into 3 carbon parts, this is another reaction that you learn next in one of the next classes. It's called a Michael addition. And now we've broken it down into 2 carbon parts. Now this is obviously very easy to make from isopropanol, right? And in fact, I think that's all that I said is start from isopropanol. So isopropanol, oxidation, Michael, Claisen condensation. So it's a much, much quicker way to make it. So I guess that's the bigger point. One last announcement before I just threw that chalk in my coffee. So on Monday, get here early. We are going to, what I usually will do is I don't like you guys just coming in and sitting wherever on exam days. We'll usually sort of lay out the exams beforehand, bring you guys in, just so it just prevents any possibility of sitting next to friends, and it just makes me feel better, like that you guys won't be cheating. So it's just one of the things that we do. So when you come in, if you come in, you can certainly come in and sit down, but I'll then throw you out into the hallway. So and then we're going to lay out all the exams and do that. But make sure that you get here on time. Remember, the subways can sometimes not be reliable, so try to shoot to get here even earlier. Make sure to get a good night's sleep, get up early, get breakfast. If you drink coffee, drink your coffee. And yeah, just make sure you get sleep this weekend, okay? All right.